Namaste, it's me Rohan Bhajankar and this is the EViews tutorial part 2. So now let's go towards EViews. We have done up to the unit test, and we have also seen the graph of parallelogram of ACF and of PACF. So now let's have a short recap on it. First of all, let's choose a variable. This first step is to choose a variable. Let's choose this CPIN. This is the first step. Let's click on it. We will click on it, and the second step is to go to view. We will go to view. This is the second step, and in the third step we will click on parallelogram, and we will click on labels. Then labels, there are three options: labels, first reference and second reference. First of all, we will check this graph on in labels, means in the log form itself. Let's click OK. This is the graph, and what we observe from this graph is that the first is we will see the function of autocorrelation. We will see this function, and what we see here is that it is decaying over a period of time. It is decaying, means that it is falling gradually, or this term is called decay, and is decaying over a period of time, and it is highly significant. It crosses this line. And the second function is partial correlation function, and this shows that the first one is significant and other lags are insignificant. This shows this process is AR1. This means that if we take its first difference, then our variable will be stationary. And this is the first clue that we can see from the parallelogram, and it is the most important figure in the time series analysis. So now let's erase this, and now from this point we have obtained a clue that if we do the first difference of this series of CPIN or CPF Nepal, then we will get the station series. So now let's go to view and let's click on parallelogram, and let's check its first difference. So finally we have arrived its first difference. This shows that the autocorrelation function is below this line, slightly touched it, but it's up to the line. In this point we can see that the autocorrelation function is sometimes positive and sometimes negative. This is the sign where it shows that the variable is stationary. And if we see the partial correlation, then it shows that there is no AR process now in this graph. And for the further, or for our test or the formal test, we will go to unit test. There are several unit tests, and we can test this from clicking view and going to unit test, and we can click on this labels, and we will click on trend and intercept. And why to take the trend and intercept? Why to take trend and intercept? This is because we will see a graph. Let's check its graph, and we will confirm it by checking the graph. Why to take trend and intercept, or to take intercept only, or to take none? So first of all, we will make its graph. We will click on view, graph, and let's check its graph, and let's copy it and let's paste on our OneNote. So now from here we can see that the graph here is intercept, and the line is trending. It's trending. So we will take both trend and intercept. So now let's go to EViews and we will take both trend and intercept in the unit root test. Now click on OK, and let's observe here we will only check the value of probability, and if it's less than 0.05 then we confirm that the variable is stationary. This means that if this probability value is less than 0.05 then we confirm that the variable does not has a unit root, or the variable is stationary. So in levels it is in levels the ADF test confirms that the variable ln is non-stationary, and the same result has been derived from the corogram also. So now let's go to the unit test and let's click on first difference. So the result changed. So now the result is it's less than 0.05, so the variable is stationary at first difference, and this is the same result that we derived from the corogram. So it is best to test from both approaches. And the weakness of this test, ADF test or any other unit test, is that the first weakness of this test is ADF or Philosopher test. Weakness is they take large samples, and if the sample is large then these test results are accurate or valid, and this is called power of ADF test, ADF or PP. This power decreases with the decrease in the sample size, and this power may be decreased by 20% or more if our sample size is less, such that we need at least 500 samples to achieve 100% of result from the ADF test, but our sample size is only 46, so the power may not be up to 100% in our case. So we must check both corogram, we must check graph, we must check the unit test, so that we can confirm our result. After this, let's move towards the OLS regression. This is the significant portion of our analysis. Let's move towards the OLS. First of all, let's talk about its theory. In OLS, what we have to deal with is its assumptions. First assumption is stationary. That is, if y equals to alpha plus beta x, then it is better to have y and x stationary. And the OLS always gives short-run result. This means that if y and x are non-stationary, then the result may be spurious. That is, alpha and beta that we estimate may be spurious. And if we want to prove if alpha and beta are not spurious, then we need to confirm co-integration. This is a bit higher level analysis in time series, and and this means that if you can prove that y and x are co-integrated variables, then the alpha and beta will be consistent or super consistent even if y and x are non-stationary. But if you cannot prove that they are co-integrated, then the result of alpha and beta that we have derived from OLS will be spurious. So first of all, it must be stationary, and the second assumption is linear in parameters, linear in parameters, and third is no multicollinearity, no multicollinearity. Fourth is no serial correlation or autocorrelation, serial correlation. Heteroscedasticity, no heteroscedasticity. These are some of the major assumptions of the OLS. And 6 is non-random. X means independent variable must be non-random. 7 is sum of error must be 0. These are some of the basic assumptions on OLS, and these are in the theory, and we must have the clear understanding of it. So now let's move towards the EViews. And since we have known that the first difference of this series is stationary, so now let's run the OLS in it. Since I have created the first difference in EViews itself, so let's choose this variable. I will choose CPI-IN, and since my dependent variable is CPI of Nepal, so I will choose it first. This means that if I choose the variable first, then the first variable is dependent as it is assumed by the EViews. And second, I will choose CPI-IN of India. This is my independent variables. Crude oil is my independent variable. Exchange rate USD is my independent variable, and government expenditure is my independent variable. M2 is my independent variable, and real GDP is my independent variable. These all are in the difference form, and these all are stationary as I have already tested it. Now I will click on open, and I will go to equation. First of all, I will select my variables. First I will select my dependent variable, and I will select my independent variables, and I will right click on it. The dialog box will appear. I will go to open, and I will click on equation. So again the next box will appear, and here the first variable is dependent variable and other variable are independent variables, and last C is constant. This is constant. We must keep C in our equation. We cannot suppress it, or it is better not to suppress it. And my sample size is from 1975 to 2025, and this is not the case because the samples is only up to 2020. So I will manage it here, and you can also reduce the sample size from here. Also you can also keep here 1990 if you want, but I don't want it, so I want it all up to 2020. So I will click on, and let's check on options. Here is all okay, and let's click OK. So the result is ready. So now the interpretation of result begins from the value of probability, and we must check the value of R square and D double test, and we will check the F statistics value, and the other values are not so important in this case because this is single model, so we don't need AIC, SC and SSQ criteria because these values are basically used to compare models. the lower AIC value is preferred, and the same result is for SC and HQ criteria. So now let's move towards the R square. R square is 0.52. It's a bit okay. 0.52 means that 52% of variation is described by these variables, means 52%, sorry, this means that the 52% of the variation, this means that 52% of variation in DCPI is explained by these variables, and the rest is error, that is less, the rest of this impact is not covered by these variables. So now let's move towards the p-value. This is very important for our analysis. This p-value means that if the p-value is less than 0.05, then only we will explain, or we will conclude that this variable has impact on it. This is less than 0.05, so CPI of India has a great impact on Nepalese inflation. And the second is USD. Exchange rate USD has also impact because it's less than 0.05. And the third, and no any variables are significant in our case. So let's check the coefficient of DCPI-IN. It's 0.588. It means that 1% rise in Indian inflation rises inflation in Nepal by 0.58%. This means that about 50% or more of the inflation in India is carried to Nepal. And this result is valid because of the following reasons. First reason is high trade volume with India. About 65% is with India alone. That is, export is about 30% and import is about 70%. And the second is pegged exchange rate. It's pegged exchange rate. So the price rise in India is easily carried to Nepal. And the second variable is USD, and the interpretation is alike to that of CPI-IN. 1% increase in the exchange rate, or if our Nepalese currency devaluates by 1%, then the prices in Nepal will increase by 0.14%. It means that if our Nepalese currency devaluates by 100%, then price will rise by 14%. This is the result of OLS. In this part, now we will check on this value, D-double test. D-double test confirms that if this stat is near to, then it says that there is no autocorrelation in our variable, and it's 2.43 in our case. So it's near to, but I don't think that this confirms more. If it's 2.01 or 2.002 or 2.05, then we can be sure that our model is free from autocorrelation. But in this case, it's a bit higher than just 2 or exactly 2. So we must check for the LM test for autocorrelation. So now let's move towards the LM test. For LM test, we will go to view and we will check on residual diagnostic, and we will go to serial correlation LM test. We'll click on it, and now its lag is 2 because the yearly data we will keep the lag 2 or 1. Let's click on OK. This LM test confirms that our model is free from autocorrelation, And in this case, we must check on this value, and it must be uh, greater than 0.05. And the rule is just opposite, because the H hypothesis or the null hypothesis is there is uh, no autocollision, and if this value is less or greater than 0.05, then we cannot reject the null hypothesis that of no autocollision. So our model is free from autocollision in this case. So now let's move towards the other. We will check the presence of heteroscedasticity in the model, and the same is we will check BPG model, and we'll click on OK, and the result is alike. That is, the interpretation is same. That is, H0 is there is no heteroscedasticity in the model. So it confirms that the model is free from heteroscedasticity. And the third is we will go to the normality test, histogram test, click on OK, and in this case we will check the value of probability, and the probability value must be greater than 0.05. If it's greater than 0.05, then we can conclude that our error term is normally distributed, and it confirms the normality principle. So now we will check on the parallelogram of QQ stats. We will click OK. It's perfectly fine. Parallelogram residuals, it is white noise. So our error term is also a white noise process. So our results are fine in this case. And again we'll check parallelogram square residuals, and we'll click on OK. This is also fine. So from this analysis, we have known that the coefficient we have derived are unbiased and they are robust. So now let's make a recap by writing on our next page. First of all, we did OLS. Second, we checked R square. Third, we checked the T stat of regressors. That is, regressors means CPI of India and exchange rate and so on. These are the independent variables. Fourth is we checked autocorrelation. From this we checked the two values, that is dw stat means Durbin version stat, and this must be equals to, and this must be equals to 2 or near 2. This must be equals to 2 for no autocorrelation. And we check LM test probability must be greater than 0.05, and 5 is we check for hetero scarcity, and for this we checked BPG test, and its result is probability greater than 0.05, means that there is no heteroscedasticity. And 6 is we checked for normality, and for normality we checked for histogram, and it's called Jarka-Bera test, JARQ, Jarka-Bera test, and the test result is probability greater than 0.05 or 5%. This is the test result of Jarka-Bera test. The seventh is residuals. We checked cologram, cologram, and we confirm the white noise process. And these 7 steps are required after having a OLS test, and this test confirms that our estimate is blue. This means that best linear unbiased estimator. And if our all the test is passed by our OLS estimators, then we confirm that our estimators are blue, or our estimates are blue. So we have done all this process in our analysis, so we can confirm that OLS is blue. Thank you, and you can ask me in the comment box below if you have any confusions.